Well, thanks very much. Are there any other comments? Okay, well, thanks very much. We're going to proceed to, I believe, to our final talk by Yalcin Efendiev.
Okay, thank you, Nick. Let me share my screen. So I will just give a, so I will give a little bit of overview of what we're doing. So it's not going to be a like detailed talk, but you can find it in many of the details in my paper. So it's called Multiscale Simulation and Machine Learning. And thank you for organizing this workshop and inviting me. I'd like to thank the organizer. Oops, so I'm stuck here. So let me say a few things, because what I do really is it's a multi-scale modeling and its connection to machine learning. Actually, multi-scale modeling is in general as a modeling. So basically, we solve the problem on a grid. Usually, we set a grid, and this is, for example, if I take a simple diffusion equation, I have a diffusion coefficient that are high in, say, black dots, what you see here, and I set a grid. So I'd like to solve this equation on this red grid, right? So the thing is that typically grid does not resolve the physical scale. For example, you can see that each grid block contains many scales in it. And then also there's another very important factor that grid does not resolve the contrast. So typically there may be jump in a coefficient. So these are physical parameters that enter. And when we set a grid, we just usually one way is that we'd like to solve the problem on a grid, particularly if we don't know what problem we're dealing with, right? For example, if I don't know what diffusion coefficient I have, which is the same thing that I don't know, but then I'm still want to solve this, for example, problem on a grid or learn it on a grid. So this is basically issues will come. What this equation will look, what equation do I have on this grid? So how can we solve the problem on a coarse grid with a desired accuracy? So this is one thing I'd like just to give a little bit background, because what I want to talk in machine learning, it's related to this. So how this type of modeling and machine learning comes together. So for example, if we look at the diffusion equation, and if I have a grid block, so in this grid block, I have many diffusion coefficients. But if I can't resolve it, it could be like representative volume and so on. What we do, we usually solve some local problems and compute something called effective diffusion coefficient here, right? By equating some averages. For example, here it shows like, I basically, if I have a piece of material, I subject it to some deformation and equate some averages that gives me like effective property of the material. so like what I showed here. So this basically in this grid block I have some effective tensor. But this is usually and these approaches are often used and are valid when the problems have scale separation, but usually in many, like what I mentioned, complex scale and high contrast, we cannot just put an effective property. So it's not sufficient for many cases. So we'd like to actually come up with a general model for some, it could be like a general framework for solving problems on a coarse grid. And we'd like to somehow see how we can relate them. How can we use machine learning also? So for now, I will just say a few things about this model, but I will try to not get into the detail because it's not the goal of this talk. For example, if I have this equation, it may not probably work with things like this. For example, this is diffusion equation, which you see here, plane diffusion that is highly heterogeneous in this in a grid that you don't see, right? So basically, if I want to solve this, the models that we derive which are rigorous and show that we have a good accuracy. We show that in fact we need to actually go to each course grid block, define first of all several macroscopic variables in certain way mathematical, and then have some connections matrices to not just near neighbor, but maybe some blocks away. So basically, this is what this model will look like. We have so this equation at the grid that basically we don't see this white, black. Now on this red grid, basically each grid block have several macroscopic UN. So this is MN continua and IJ is coarse grid block. So this is actually a bit, let's say, not traditional, and something like this not been done before. So typical approach always boiled down to some type of a regular scale. And in fact, we show, this is probably the first thing that we show how to build this model, and we can show that actually we can guarantee that they have a numerical accuracy order H, where this C is independent of physical scale. So this type of basically methods that we've been developing. And the question is, how can, I mean, I will say maybe a few more things about how we come up with this method, so it's not, it doesn't look like it's a magic. So before I go, like, let's say that, for example, if I in this axis I have what I call data relevant accuracy. Here I have a complexity. If I take a model too less complex, like for example, the first model I showed you, I put effective property, then basically I can make a large error. So technically, if I'm learning or inverting that model, I mean, there's probably no need, because all the errors in the data will end up in a model. So we don't know what we get. So in that sense, we always have to like have a, that's the reason I like to show this slide, that we need to have some type of models that are within the some desired accuracy of the data. And such thing, actually, we can use it for nonlinear problem, but I'm going to skip. This is like a two-phase flow, and I will show you later how we do this type, the model I showed you for the nonlinear problem. But before I go to that, let me tell you how we come up with those model I showed you. How did we derive them? So actually, the derivation, it goes back for many years that this type of project, we started with something called multiscale find element, where we try to solve the equation on a coarse grid by building some finite element basis function. So again, what you see here, the diffusion coefficient, highly variable. And what we're trying to do, we're trying to build a multiscale basis function for each node. For each node, instead of just having regular piecewise linear basis function of finite difference, we try to build this heterogeneous basis function. This is basically was for us maybe a gateway to find this accurate method, because this type of approaches, once I write down the solution, first of all, this basis function play a role of macroscopic parameter, but once I write down this as a solution, then I can compare this approximate solution with exact solution on a fine grid. So this type of approach is basically was a beginning, and that's what led us to understand that, first of all, one base is not enough. So we need more bases to represent this macroscopic variable. So in a many years later, we designed this methods where we have a more rigorous way for general structures to identify this multiple basis function and show that they have to have a support greater than the region. So basically, these basis functions play the role of this macroscopic variable, and this bigger support that we need to make sure that the method converges. We need this bigger support. It's this some type of non-locality. So this is basically some type of a model. This is a framework that we use, and then we relate this basically, if you look at multi-scale methods, typically this coefficients. I mean, you have a basis and you have a coefficient without the basis. So what we can do, we can try to modify the basis so they end up being some physically relevant quantities. So, so in nonlinear problem, what I showed you maybe looks like this, and you already see that this is to get this rigorous, accurate models from the it gets expensive, because if I like to compute, so if I have a nonlinear partial differential equation, so where you have a nonlinear parameters, like could be relative permeability, could be many things. So to compute that for a target grid block, so what we do, we have to solve problems, these nonlinear problems in a bigger domain and constraint problem for this macroscopic parameter. So in a sense, it looks like a bit like the following, that I need to take a bigger region and solve many problems. And first of all, identify macroscopic variables. So again, this is something we do through some local spectral problem, which I skipped it. But this could be like each block may have 2, 3, 5, 7, some type of macroscopic variable, and then we solve a problem in a green region to identify the nonlinear parameters as a function of macroscopic variable that are in a green region. So this is one point, for example. You see, so this is how we build a macro scale model, and you can see that here, how do we need to use machine learning, because if I want to compute my effective fluxes or coefficient in this block, which depends on macro scale 5 by 5, 25 blocks, each may have several macro scale variables, and this is, so we need a training. We need to solve many local problem and train this local problem. So this is one place where I call it local training. So so this is many applications here. Let me skip this. This is a detail of this. So let me go back now to this in machine learning. How do we use it? So in these problems, we have we can think of input in this model problem, for example, in this problem. So input is a forcing boundary condition, could be this coefficient, and typically output is a solution or effective properties of a model. And then we build this input output relation. So first thing, what I mentioned, maybe it's here, but multi-scale model. So what I showed, what I mentioned, that we basically can use this machine learning and deep learning algorithm to learn this effective property. So this is kind of like a local learning. And this is somewhat basically necessary for this complex multi-scale problem, because effective fluxes depend on many parameters. It's a big region. We cannot just build a lookup tables or anything. Which I come here, basically, this model themselves, you saw it's expensive to compute. So we can write their forms, we can see what they are, but computation can be expensive. And this is one place also machine learning and deep learning we use, and important is to train this. So we don't have to compute all these parameters, but instead we learn the models. Because once I have a form of a good model in that first graph, one of the graph I showed you, I can learn it. And there are other questions basically which we answered in our other papers, that what does interplay between deep learning and reduced order model. So basically, like maybe this was motivated with more computer graphics or something, where this deep learning algorithm can extract the features. So question in models, what features we extract. So we had this idea that these features actually related to these macro scale features, but can we show it? And this is something we managed to show in some simple problems. So can machine learning be used in multi-scale inversion and UQ? So here also we use machine learning in our multi-scale inversion and uncertain quantification. For example, in MCMC algorithm, we train the input, we train the we build a hierarchical model. We have some type of a multi-stage MCMC algorithm, and we use deep learning or machine learning algorithm to speed up the MCMC calculation. So let me just maybe in a more formal way to show it. For example, this is what I was saying, one of the things, local learning, which I will show some details. So this is basically if I have effective property, which I showed you, it depends on U bar. and we build networks. So this is typically, again, we use many times we use known architectures and maybe modify, which I show you a little bit, but modify them, particular like cutoff function and things like this, because they are more, for example, for nonlinear upscaling, they're more relevant to use what we have. So use the available data. We want to predict the coarse grid models, and this is what I was saying, interplay between deep learning. We show that the layers of deep learning predict coarse grid models. So there's some detail, but I'm gonna maybe go over fast because I'd be happy to talk this offline. And so, so this is deep learning coarse grid parameters. So there's a lot of little things also appear here. For example, once we build these local models, we have some type of idea, the structure of the model, like which grid block talks which grid block, and so on. Of course, we can use all this information in the learning algorithm. So this is what basically how we can use connectivity, how can we use the basically setting up the parameters, the neurons and so on in the activation function. We can use this information. So this was it's one of the earlier papers. It shows like how we can use spatial locality in this case, I think it was CNN, the structures, and they predict, like if we have a fully connected and locally connected, we can get about the same accuracy. So it saves us because we have a good understanding of our models, which is true. And here's a example problem. It's a simple. Mostly these are test problems because we check our theory. So these are some initial permeability fields. Simple for some fracture, we shift them, assume that that's a true one. And there's some also other things that goes in here, like we use a mixture of the simulated data and observed data. But again, observed data here in this example basically come from unknown permeability field. This is learning coarse grid parameters. Again, this is maybe it's simplest because it's and a very important part. This could be in stochastic cases. For example, if I have a stiffness matrix and I can run for some permeability fields, learn for others. So build the networks for that. And this is what I was saying. For example, this is a reduce order. This is the basically here we construct we use the soft thresholding, and we show that the learning algorithm actually can recover reduce order model. So there is this relation between this, and then we apply it for some type of nonlinear problem in this case. Maybe I try to wrap up. So this is, as I mentioned, multi-scale inversion. So we have upscale models here. What I mentioned that they are not accurate. Like when we have an affected property, we can use an appropriate like reduce order model, which begin a degree. Machine learning. This maybe I skip. And the last thing I just say what we do, and maybe finish with this. So we mostly look at what I mentioned. This is local. What I would say local machine learning, when we learn these local parameters, and of course there's a global machine learning. You can learn the global model, right? And then there's a way you can also try to combine local global. Actually, this is something. This type of terminology is something with Eduardo Gilden been developed for model reduction, but it could be also done something similar here. We use the machine learning for sampling around certain quantification. So when we have a Markov chain Monte Carlo type algorithms, each sample is expensive to make a decision, accept, reject decision within Metropolis Hastings. So our earlier work on this was to use some type of screening procedures, for example, use reduced order model to decide whether we run more expensive model and so on. And we can prove that this multi-stage MCMC samples posterior rigorously, but now we can also remove this coarse grid step and replace it with machine learning. We use some of the things we use machine learning for clustering. So this is for stochastic problems, for the forward problem. When we build a reduced order model, for example, if I have a grid block, within a grid block, I see many permeability fields. If I try to build a basis or something for all of them, it could be just overkill. So we can cluster and build them and then use them. So this is also, and we'll look at different applications. This kind of framework type of thing can be used to solve different problems. And that's it. Thank you.
Thank you very much for the talk. Are there any questions? Either feel free to post them in the chat or ask directly over the audio.
Okay, let me see. Let me stop share. Let me see if there are any question.
So do you, I'm not sure if you were able to attend other talks.
Yes, I had some meeting in the morning, but I attended.
Right. I wonder if you have any sort of comments about, connections between, the approaches you're taking and some of the other talks in the program. I mean, I know, of course, you're
Yes. There is probably maybe approaches Eduardo doing. I missed his talk because I had the meeting, but the approaches I'm sure he's taking. There is some relation, and I think maybe also with the with the rock team approaches, maybe there's a. I mean, I think he mentioned some of the preserving preserving some properties in the machine learning. So this is also a very important thing for us. But I guess what really differs what I'm doing in a sense. So for example, it's more really local modeling, deriving and it basically needs it needs its own. I didn't talk much about it, but it needs its own network architecture. It needs its own thing. So it's in that sense, it's different probably, and the models, yeah, and they are basically still a grid-based models, but some type of it's not very fine detailed grid, but the grid is coarse that we can handle this problem because we don't have a huge number of parameters. This is maybe also more suitable like when we don't have a huge number of data, like for typical, for example, probably it's also true for subsurface problems or something. We cannot like afford solve. I mean, these still coarse grids are quite large, but they're not at the resolution, say at the pores or something, right? They're not. This is what. So in a sense, yeah, it is related. It is the combined physics and machine learning. But a certain aspect also makes this for what I mentioned as local when we do the way this rigorous upscale and rigorous multi-scale models end up with that. We see that, I mean, this like has to have a machine learning in it, because we cannot compute these effective properties. They are functionals of many parameters. They're training, they need to be trained and so on.
Okay, thank you. Are there any further questions? Okay, well, thanks, Yashim. Thanks very much for that talk.